Alright, welcome to another podcast. In this episode, we're going to be taking a look at an example of proving something via weak induction. And the example that we have here is we're making a claim that there's a certain ATM that the only bills that it'll output are $2 bills and $5 bills. And the claim that we're making is if you give it any dollar amount or request any dollar amount greater than or equal to $4, this ATM will be able to make change for it. So it's just sort of an example to highlight this. Let's start off by saying, okay, $4, that's expressible as 2 plus 2, so it could make change for that. If you requested, let's say, the next interesting one would be something like, let's say $13. So if you requested 13, it's $5 plus $8, and $8 would be 4 2s. So it could make change for that. And the question is, can we prove that this ATM would be able to make change using only 5s and 2s for any dollar amount greater than or equal to 4? So thinking of this in terms of the notation that we used in the previous video about the induction machine, our propositional statement Pn is the ATM can make change for any amount n greater than or equal to 4. So this statement depends on the value of n, and as long as n is greater than or equal to 4, the ATM will make change. So there's a couple of steps, if you recall, from the previous video about how to make induction work. And the first step, step 1, is the base case. So I have to prove the base case, which in this case, the base case is n equal to 4. That's the smallest amount, the base amount, the starting amount that we'd have to look at. And you need to be very careful here about how you prove this. You need to start off by saying $4 is equal to $2 plus $2. This is one of those subtle points. You wouldn't want to reverse this. In other words, you wouldn't want to start off by saying 2 plus 2 equals 4, or else you're kind of using what it is you're supposed to be proving. So I'm supposed to prove that $4 can be broken down, not that 2 plus 2 equals 4. So I know that's a little bit nitpicky, but it does show up on other problems where that will cause issues, and I'll try to explain that in class when we run into those. But here this checks out. The base case checks out. I can express $4 as a sum of two $2 bills, therefore it would make change in that case. So now the next step, step 2, is you have the induction hypothesis. The induction hypothesis would state the following. You would say something like, suppose P of n is true for some n for some, let me put it this way, for some, so let's suppose pk is true for some k less than n, k greater than 4. Meaning that there's some specific value that we know that it's true for, and that value is some arbitrary number less than the number n, but greater than our base case of 4. Then we must show that pk plus 1 is also true. So our inductive hypothesis is that the ATM machine works for any dollar amount up to k dollars. And we've got to show that if it works for k dollars, then it also works for k plus $1. Now here's where things get a little bit more interesting. So S3 is I need to show that pk plus 1 is true. Well, I'm going to divide this into cases. Case 1, and this is often part of an induction proof, is that you have to divide it up into cases. So proof by cases approach is a good approach. So case 1, let's suppose that the k plus $1, or let's suppose that the k dollars contains a $5 bill. So in other words, we know that it was able to make change for the k dollar case. Let's suppose that that k dollar case contained a 5. Well, if that's true, then I can replace the $5 with three $2 bills to make change for the k plus $1 case. So in this case, P of k plus 1 holds. So if my k dollar return contained a 5 somewhere in there, then I can exchange one of the $5 bills for three $2 bills, thereby giving change for k plus $1. Alright, the second possible case is, you guessed it, that the k dollar previous does not contain 5. In other words, the k dollar output contains only $2 bills. So if it contains only $2 bills, then since n is greater than or equal to 4, there must be at least two $2 bills. Replace these with a $5 bill. This gives the change for the k plus $1 case. So P of k plus 1 holds in that case as well. So that in either case, so therefore, in either case, Pn implies Pn plus 1. So the statement Pn is true for all n greater than or equal to 4 by induction. Induction on n. So the basic idea here is we established the base case for the smallest amount that we wanted to consider, which was $4. Our induction hypothesis said, okay, suppose that I'm able to make change for any dollar amount up to k dollars. Show that having that knowledge allows me to also find it for k plus 1. Notice we used the base case as a part of case 2, where we knew that since it was greater than or equal to 4, then in the base case we have at least two 2's that we could replace with the 5. So the base case showed up here as well. And in both cases we were showing that pk plus 1 holds. So for all values of k up to n, we've got Pn implies Pn plus 1. So by the induction hypothesis and by the induction machine, just the general machinery of what we're doing here, go back to the previous video if you want to make sense of what I mean by that, then the proposition Pn that the ATN can make change for any amount n greater than or equal to 4, that's true for all n greater than or equal to 4 by induction on the value of n. So the induction process always occurs on the thing that's being iterated according to the natural numbers. So n here, the dollar amount, is a natural number because we wouldn't have a $2.2 amount since we're just talking about whole dollar amounts. All right, thank you for watching.